The Italian multicenter study on hyper-alpha-small-A lipoproteinemia is a study on predictive profile of cardiovascular risk in patients with hyper-alpha-small-A lipoproteinemia in isolated or combined form by means of descriptive analysis of genetic polymorphism, isoform of apo-small-A, and the cholesterol loading capacity. LP-small-A is composed of an LDL particle with an ApoB covalently bound to apo-small-A, which is derived from cradle 4 and 5 of the protease domain. There is an inverse correlation of copy number variation length with LP-small-A levels, and this inverse correlation is explained by the processing of apo-small-A isoform during transit through the secretory pathway from the hepatocyte. Shorter ApoA isoform are secreted more efficiently than longer ones. So, ApoA size polymorphism is a major predictor of LP-small-A levels, contributing between 14% to 70% of the variation in LP-small-A concentrations. Increased LP-small-A levels are present in 25% of the population, and they confer an up to 2.5-fold increase in cardiovascular disease risk. ApoA isoform with small molecular weights seem to expose to a higher cardiovascular risk than larger isoform due to different rate of oxidation of the molecule, and some LPAG invariants are strongly associated with both an increased level of LP-small-A lipoprotein and an increased risk of coronary disease. In the Procardis cohort, were identified two LPA variants that were strongly associated with both an increased level of LP-small-A and an increased risk of coronary disease. This finding, provides support for a causal role of LP-small-A lipoprotein in coronary disease. On the other hand, serum lipoproteins influence cell cholesterol content by delivering and removing cholesterol to from cells. In this experience, serum macrophage cholesterol loading capacity was evaluated by measuring the capacity of patient sera to deliver cholesterol to human macrophage. The serum was obtained before lipoprotein apheresis and immediately after apheresis and 2 days after apheresis. The black bar show the macrophage, the macrophage cholesterol lowering capacity of the pre-apheresis serum was significantly higher compared with that of normally paid endemic serum that is in the gray bar. Immediately after lipoprotein apheresis, serum macrophage CLC was immediately lowered, and a similar found was 2 days after lipoprotein apheresis. Cholesterol loading capacity of human macrophage may change with different levels and different isoform of LP-small-A. The aim of our study was to evaluate the genetic LPA polymorphism, isoform of ApoA, and the cholesterol loading capacity in a cohort of patients with hyper-LP-small-A lipoproteinemia, isolated and combined form, and cardiovascular disease, chronically treated with lipoprotein apheresis, and to compare macrophage cholesterol loading capacity measured before and immediately after a single lipoprotein apheresis session in the cohort of a patient on lipoprotein apheresis treatment. We enrolled adult patients with hyper-LP-small-A lipoproteinemia, cardiovascular disease, chronically treated with lipoprotein(apheresis), and a control group of patients that were not submitted to lipoprotein(apheresis). They are the Clinical Center, Roma, Verona, and Pistoia, and the Laboratory Center, Genova and Parma. We enrolled 34 patients, 18 patients on lipoprotein treatment, and 16 control group. LP(a) median at baseline was 121 in the lipoprotein(apheresis) treatment group and 103 in the control group. We show the clinical demographic characteristic of the 5 patients from Verona on lipoprotein(apheresis) treatment. All patients present a coronary disease before treatment with lipoprotein(apheresis) and peripheral vascular disease. No patient have new coronary events after the beginning of lipoprotein(apheresis). In this slide, the control group from Verona and 1 patient from Pistoia. One patient from Verona had a myocardial event. The other patients have bilateral carotid stenosis. The group on lipoprotein(apheresis from Rome is an important group with coronary disease before the beginning of lipoprotein(apheresis, and 3 patients have a new event during lipoprotein(apheresis. And the control group from Rome, patient with coronary disease and with peripheral disease not in treatment with apheresis. The result of our data will be presented in the next communication. Thank you for your attention.
Thank you very much. I think that's marvelous. So what we'll do is Professor Pisciotta, is that right? Pisciotta will present the results. Lydia, welcome.
Thank you very much, and thank you, Claudia, for the possibility to be here and present the preliminary results of the genetic analysis of the cohort of our patients with hyper lipoprotein small a. Thank you very much. My disclosure. And we know that LP(a) is implicated in pathogenesis of atherosclerosis. And recently, with my new research group in Genoa, we demonstrated that in 180 patients with severe carotid artery stenosis undergoing endarterectomy, the serum lipoprotein(a) predicts acute coronary syndromes in patients. So it's very important to determine lipoprotein(a) in assessment of the cardiovascular risk. You can see here the gene coding lipoprotein(a), the gene LPA localized on chromosome 6. The strong role of genetics in determining LP(a) plasma levels is responsible of the particular distribution in population, not normal but very asymmetric. This is the structure of LPA gene. It's very complex. Because shares a high sequence homology to human plasminogen, but clinicals 1 to 3 of plasminogen are deleted. We can observe an expansion and differentiation of the Kringle-4 domain that resulted in 10 different types of Kringle-4 domains, all specific in their amino acid composition. Further expansion of one of the Kringle-4 domains resulted in the multi-allelic intragenic copy number variation nominated in the precedent presentation. The other Kringle-4 encoding domains, the 1 and the 3 to 10, are present only in a single copy. Several polymorphism non-sites are described in literature, and some of them are associated with cardiovascular risk. In our laboratory, we analyzed DNA of the patients with the next generation sequencing technique, based on a custom AmpliSeq panel designed for sequencing human genes related to lipoprotein metabolism and was performed with the Ion PGM sequencer. You can see here all the genes present in our panel. We have LPA genes, but also a large number of genes implicated in lipoprotein metabolism. Here are the characteristics of our population, in particular the cases in apheresis treatment and the control. You can see that the levels of lipoprotein A is higher in cases than in controls, and is higher in females than in males. If we observe in our population patients without carotid atherosclerosis and without coronary artery disease, they presented lower levels, but without reach the statistical significance in the difference. In our, Okay, in our population, we identified only 5 of the polymorphism described in Procardis study, and you can see in evidence the polymorphism we identify in our patients. In particular, the first is one of the 2 polymorphisms with the strongest association with the coronary artery disease, and we identified this polymorphism in 2 cases and 1 control with allelic frequencies 0.04 more frequent than the frequency in Procardis study. We identified that the second polymorphism is an intronic variant in 7 cases and 7 controls in our population. The other intronic variant was present in 5 cases and 1 control in heterozygous status. And the last is a missense mutation on exon 26. In silico analysis, the results not pathogenic, but in Procardis study is associated with a little increase of coronary risk disease. In our casuistic, we identified this mutation in 4 cases and 3 controls, and 1 control was homozygous for the rare variant. Now, I'd like to show you the distribution of these 5 variants in cases and control. You can also observe that in controls, there are no patients with more than 2 variants. And in the group of cases, some patients have 3 and 4 variants together. So we can conclude that cases present a more polymorphism variability in their DNA. And if I compare the lipoprotein small a levels in patients without variant and the patient with 1 or more variants, we can observe an increase of levels in patients with more or 1 variants, but the statistical significance is not reached. In our patients, we also identify some benign missense or silent variants. And the distribution of these variants are similar of the first 5 variants. Controls presented less variability than cases. But in this case, if we compare the levels of lipoprotein small a, we can see that patients without variants, benign variants, presented a upper level of LP small a. What explanation? But probably these variants may be protective and maybe an effect of lowering the levels, or another explanation is the presence of a very important value of lipoprotein small a, 435 in 1 patient without any benign variant. And you can see the important standard deviation for this value. Another important point is that only in recently 2 additional genes were implicated into lipoprotein small a metabolism, and they are ApoE and PCSK9. And in particular, ApoE E2 form is associated with 15% lower healthy small a concentration, whereas the effect of ApoE4 is controversial. And mutation loss of function of PCSK9 are implicated in lower levels of LPA concentration. So with NGS sequencing, we can in future examine in all our casuistics the influence of other genes such as ApoE and PCSK9. In conclusion, preliminary data confirmed that LPA's gene is extremely polymorphic. This is the first systematic study on Italian population. The protective role of genetic variants of LPA gene versus cardiovascular risk need to be confirmed considering a global evaluation of phenotype and genotype. And other genes such as ApoE and PCSK9 will be evaluated. Future studies should also explore the relative adjunctive effects of PCSK9 inhibitors for innovative drugs such as apolipoprotein antisense and APHERESIS in patients with elevated LPA. And we think that our study may increase the knowledge in this particular field of research. Thank you very much for your attention.
Thank you very much, Lydia. So just to continue in the trend, we will have the discussion at the end. So to continue this important study of the metamelic, Federica Vaccondio will now present.
Thank you very much.
Okay, so thank you very much for giving me the opportunity to talk today. Well, as you can see from the title of this presentation, well, we tried to describe by means of tandem mass spectrometry APO small a in human plasma in terms of either concentration and presence of different isoforms. So just first slide to show you, just a few information regarding the advance and the introduction of mass spectrometry in the clinics. So we have to go back at the beginning of the 80s to see the first application of mass spectrometry within the analysis of clinical samples. And it was mainly related to small molecules, volatile molecules. We are talking about drug of abuse, steroids, and screening for newborns. And then later on, with the introduction of liquid chromatography coupled to spectrometry, well, and to the coming of the omics techniques, of course, we have got the big improvement in the applications of mass spectrometry to all different clinical fields. And so that nowadays we have some cutting-edge application regarding, for instance, knives which are guided by the use of mass spectrometry for surgery and other applications. So it's quite a big improvement in this sense. And talking about the analysis of complex protein mixtures, so when we are dealing with human plasma, of course, we have got a very complex mixtures of protein. Well, mainly we can identify two approaches. One is related to gel-based approach. So we start basically from cells, cultures, all tissues or organs. So we extract the proteins by different procedures. We separate them by means of two or one-dimensional gel electrophoresis. We digest the single spots that we are able to stain and excise. And from the peptide mass fingerprint of the peptide that we obtained after triple digestion, okay, we can identify a series of proteins. So this is the typical gel-based approach, which is the classical proteomic approach. Nowadays, we also have the so-called gel-free approaches, in which basically the electrophoretic separation is instead substituted by HPLC-based techniques. So basically, chromatography is of peptides coming from the digestion of a mixture of proteins. Of course, both approaches has got its own advantages and disadvantages. So briefly, sorry, so it's really fast. I cannot get where I want. Okay, so let's see. No, really, it's crazy. Okay, here I am. Okay, so of course, when you are coupling a gel electrophoresis, it is clear that it is wonderful if you want to identify different isoforms of a certain protein, but of course you have to deal with the complexity of a protein mixture. So if the complexity is too high, well, you cannot apply gel electrophoresis in a proper way. The other aspect is related to the quantitative applications of gel electrophoresis, because also in this case, one spot can hide different proteins, and this, of course, doesn't have quantification. The other aspect is related to the fact that many hydrophobic proteins, such as ATP, cannot enter efficiently in the gel. And so the quantification or the relative quantification sometimes can go in the right way. On the contrary, well, if you go for gel-free separations coupled to mass spectrometry, also in this case, well, the principle by which a single chromatographic run can resolve the complexity of a human plasma proteome, of course, is something very simplistic. So also in this case, we are dealing with a mixture of hundreds, sometimes of thousands of peptides with very different physicochemical properties. And so also in this case, if the complexity is too high, we may get to different results. There's also another aspect related to the concentration of the protein, because if you have got a small abundant protein, then the digestion of that protein is very low, and therefore you need time to get it digested fully. Okay, just to give you some hints. So I'm worried that to change this. Let's see. Okay, I don't know why. Okay, so I will go briefly on this part because, of course, the other speakers have already described this. So what I would like to underline, just from my point of view, from an analytical point of view, is that, of course, this Kringle 4 type 2 domain leads really to a huge heterogeneity within the protein. So Lydia first was talking about the genes. Well, of course, if you're talking about the protein, well, you get with molecular weights which goes from less than 200 kilodalton to more than 600. So we cannot deal with just one single analyte, but we have got really the most heterogeneous protein within human plasma. So it's really very specific and very peculiar of this apheresis. So, okay. So to resolve this, say, complexity, so the golden approach is a high resolution electrophoresis. Okay, there's a big problem related to it because just imagine these huge proteins and that the small size of a Kringle 4 unit. So it's about 17 kilodalton over a protein, which is indeed very, very big. So you have to get a high resolution separation in order to resolve the different bands corresponding to the different isoforms. As you already know, the majority of individuals express at least 2 different alleles of aPHERESis. Sometimes we've got just one single band, but most of the times we've got 2 bands or even more. The other aspect related to electrophoretic separation is that APHERESis mobility is peculiar also in this sense, so sometimes the classical calibrants are not able to show the same electrophoretic mobility, so this can be a problem. Another problem related to measurements is the aspect related to the antibodies that are employed to quantify and to measure these proteins in plasma, because there's this nice paper that suggests that, okay, you have to be very careful regarding the specificity of the antibody, okay, so that if your antibody is recognized as a repeated sequence as an epitope, of course you can get either an underestimation or an overestimation of the LP small a concentration in plasma if compared to monoclonal antibodies recognize the constant domain within APOA. So basically, the idea here is to take the same common calibration, it is the same common calibrant which has been approved by the International Federation of Clinical Chemistry, and also be sure to use an antibody which is unaffected by the polymorphism of APHERESis. Okay, so what we tried to do in our lab was to apply a HPLC tandem mass spectrometry approach to the analysis of human plasma. So to go a little bit quicker, I will just show you the protocol that we followed. Okay, here it is. So basically we started from a small volume of plasma or serum, and we submitted it to a classical proteomic protocol, which is reduction, alkylation, and digestion overnight with a high specificity trypsin, okay, which is the protease we commonly use for this type of applications. So at the end, the digestion is stopped, and the samples, after centrifugation, are injected into the HPLC SMS instrument. What we are looking for are the so-called proteotypic peptides, which are typical of that specific protein within human plasma proteome. So it means that, okay, if you go on a line with the available databases, oh God, my God, I'm really sorry. It's quicker than. Okay, but it's really quick. Okay, so if you go online and you search, for instance, for one of the peptides that we followed, okay, well, what you get at the end, that they belong just to a, okay? So you have to be sure about it, because in this way, you can be sure that the concentration of the peptide that you measure are representative and are proportional to the concentration of the protein that you want to monitor. Which peptides have we decided to follow? So basically, okay, I don't know why. Sometimes it doesn't work and sometimes it works. Okay. I'm not able to let it work. I'm really sorry. Okay. Yes, can you
give you the classical one?
Wow, yes, it would be greatly appreciated, because otherwise we can stay here for.
This is a real classical one.
Okay, so let's see.
More fun.
Okay, so we go back. Wow, this is great. Okay, sorry for that. Anyway, so just to show you here, we've got so the two peptides that we have decided to follow. As you can see from the sequence of an APO which is published in the UniProt database, well, basically there's one peptide which is present in the constant part of APO, and the other one, which as you can see is repeated a series of times, because it belongs to the Kringle 4 type 2, okay, which is the one which gives, of course, the polymorphism. Okay, so we try to follow these two peptides. And basically, okay, this is the chromatogram that we got while we try to elute the peptides and their labeled internal standard within our HPLC SMS instrument. So as you can see, we have got the GTYS peptide, which is the repeated one, so it should be proportional actually to the size of the ApoA we are measuring. Then I will tell you a little bit about it later on. And the other one, which is the LFLE, which is instead characteristic of the constant domain of the peptide. So in principle, if you go and follow these two peptides, you should have indication related to the concentration and the size, which is an average size, unfortunately, because we have got in plasma more than one isoforms. But anyway, at least it's an average size of our population of APOA. So let's see if or what we got as a result. Okay, well, another interesting thing is that, of course, things become more complicated when we move from the mixture of peptides up to a sample of plasma, okay? So as you can see, well, you have got a series of other peaks which correspond to isobaric peptides and isobaric interferences, but fortunately, they don't have the same retention time in the chromatographic run. So hopefully, we can be rather confident that the peptide we are measuring are indeed the ones that we want to follow. Okay, what we wanted to check, first of all, was the linearity of response. So indeed, if we decide to spike our plasma sample with non-detectable levels of a, with known amount of recombinant proteins, with known Kringle numbers, do we get a linear response? Well, we are really grateful to Professor Angeles Cagno from INSERM in Paris, because he gave us 3 different recombinant proteins, as you can see with the 10, 14, and 18 Kringles. And we were able to add them, so to spike the human plasma with different concentration of these 3 recombinant proteins. They had also their own concentration. And we digested them in human plasma, which didn't give interferences at the retention time of our analytes, to see if there was any linearity of response. And indeed, it seems that, okay, the ratio of the peptide, which is proportional to the concentration of ApoA, is directly proportional to the concentration of added protein. So there's linearity over there. So as the response is linear within the range that we have measured, then we try to analyze the samples, the human plasma samples of the multicentric study. And this is what we got. Okay, as you can see, well, especially in the first regression, well, we've got 1 point, which is the one which has the highest level of APA, which of course drives the whole correlation. anyway, if you leave this point out, well, still, okay, the correlation coefficient is not that bad. I mean, at least considering that we are dealing with, in this case, just the area of the peptide proportional to the concentration. And in this case here, we got the same thing with the ratio between that peptide and its internal level of standard. So the correlation is still there, even if we exclude the point which indeed drives the correlation because it's the most different from the others. Okay, so even if, I mean, the data from immunoassay, of course, are related to LP small a, and instead we are measuring the APO small a because we are dealing with just the peptide and not all the other components of the LP small a, well, there's a correlation between the data. So this is nice, I mean, after all. Then we go to the problem related to isoforms. Okay, so also in this case, we employed different concentrations of our recombinant proteins, which were digested in plasma. And what we observed is that if we calculate a different concentration of the protein, the ratio between the two peptides, so the peptide which is proportional to the number of kringles present within the, of course, the average APO small a present in the plasma, and the peptide proportional to the concentration, what we get is a ratio which is rather stable. Okay, the standard deviation, maybe it's at least in the central one is a little bit higher. But anyway, there's a increase which is proportional. There's a direct proportionality within this Kringle number range between the ratio of these two peptides and the number of Kringles. Okay, so we decided to employ this linear relation to calculate the mean, the average Kringle number within our plasma samples. And what we got is this. Okay, so here is the frequency of the mean, the average Kringle number that we get in our patient compared to the frequency of them. Of course, the problem related to this approach, well, it had already been observed in a communication from a researcher from Merck in 2014. And we, unfortunately, we observed the same in our patients. I mean, when you compare when you check for the correlation between the Kringle number and the concentration, which should be indeed an inverse one, okay, the slope of this correlation is clear if you use the electrophoretic method, which allows, of course, to separate the different population. But when you get to an average Kringle number, like the one that our HPLC MS method gives, well, you see a rather flat response. So basically, you lose the dependence over the concentration compared to the Kringle number, because it is a mean Kringle number and not a Kringle number representative of the two different isoforms which are present. And so this is why we have to talk about average. One interesting thing maybe is this one. So even if we are dealing with an average Kringle numbers and an average size of our population, we also wanted to check if the pre and post apheresis sample were different. Okay, so of course we see a decrease in the peptide corresponding to the concentration of the ApoA, and regarding the ratio, instead, it stays, well, apart from one case, it stays rather stable. So it doesn't seem that, I mean, the distribution, the size distribution of the population of the APO small a is affected by the apheresis treatment. Of course, we cannot say that much because, okay, the statistical significance is related to 5 patients. So we need to increase the number, and indeed it is what we are going to do later on. But this is the result that we obtained comparing the areas of our peptides and calculated the Kringle number from them. So, in conclusion, what we tried to do was to develop an HPLC MS treatment for our plasma samples in order to evaluate within the same run concentration and average Kringle number in our human plasma samples. Of course, we will increase the number of samples related to pre and post apheresis in order to see if this relation is still there. And what we could also do, well, it could be interesting to enlarge the relationship between the ratio between the two peptides and the Kringle number to other recombinant A at higher size in order to see if the linear relationship is still there. And the other thing is that, of course, all the HPLC multiple reaction monitoring approaches can be multiplexed in general. So if you've got proteotypic peptides to follow, well, basically in one run you can follow more than one analyte, and you can, if you've got the proper calibrant, monitor more than one single ApoA or Apo other lipoproteins within the same run. Okay. So thank you very much for your attention, and of course, thanks to all the people involved in this project. Thank
you. A very clear and exciting presentation, state of the art, and you've just seen a photograph of her bottom right in the last slide. This is Elda Favari, who's going to present the fourth arm of the multi-center stent.
So, of course, I want to thank Claudia, as everybody else here presented, but also I want to thank Claudia for the passion that she put in our multicentric study, and the fact that she's inspiring us to move on in at least our results. What I want to reassure everyone, the title looks similar, but the tough work it has been done by my colleagues Federica Vaccondio, that she presented already. I did actually the easier part of the job, so we do. My part is much easier, and maybe for you it's much easier to understand. What I want to focus is heterogeneity. Actually, for more than 10 years, I'm working on HDL, and it's not the topic of my talk today, but HDL quantity, it has been high from several years, I think, the quantity hides the heterogeneity. And when we move from quantity to heterogeneity, so quality of HDL, we discovered that HDL had a different functionality. So why I'm talking about heterogeneity? Because as we heard already, Apo small a is a very heterogeneous particle. And we heard already this heterogeneity is done by Kringle 4 type 2, which is repeated several times in some case or not. So we have another, in this case we have a pro-heterogenic particle which is very heterogeneous. So at this point my question when we start with the project was, is this heterogeneity affecting the pro-heterogeneity of this molecule? So I went over the epidemiological study that we heard. I found this paper by the Copenhagen Art Study Group in Denmark, and I found the fact that they discovered that less you have the concentration of Kringle 4 type 2, the more you have risk of developing cardiovascular disease. This is a genetic observation that confirmed the epidemiological study. So at this point, I said, okay, what about the functionality? And talking about the functionality, we arrived to our multimedia multicentric study on hyper-LP small a. And I said, okay, what is the functionality of the pro-atherogenic lipoprotein? He is to increase the amount of cholesterol in macrophages. So more you have this lipoprotein, more modified lipoprotein, more you have macrophages that are taking up this cholesterol becoming formed cell. So the macrophages is the principal actor in the development of atherosclerosis plaque. So we have oxidized modified LDL taken up by macrophages, and we have the progression, the formation of formed cell, and the progression of the lesion. We know then LP small a binds to the macrophages, so we ask why not to measure the functionality in terms to load the cell with the cholesterol. Intracellular cholesterol homeostasis is an equilibrium between cholesterol in and out from macrophage. LDL brings cholesterol, HDL brings out cholesterol. So we have a pro-atherogenic particle and we have an anti-atherogenic particle. In the first case, we measure cholesterol loading capacity, CLC, which is a pro-atherogenic function. So we expose a cell to human serum and we measure how much cholesterol is taken up by the cells. In a second case, we expose macrophage or cell models to serum and we measure how much cholesterol is going out the cell, which is not a part of this topic because we had these pro-atherogenic particles, so we focus on the cholesterol loading capacity. We took THP1 human monocyte, derived them with to the macrophage. We expose it to the human serum 5% for 8 hours. And then with the fluorimetric assay, we measure the cholesterol mass in terms of microgram cholesterol per milligram protein. So this, it has been published already in different papers, is a method to directly measure the functionality of serum to load human macrophage with cholesterol to generate formed cells. Okay, now some results. Of course, first of all, I just would like to show what is expected at the apheresis and serum lipid values. Apheresis affect the lipid value of the lipoprotein, either pro-atherogenic lipoprotein or anti-atherogenic lipoprotein such as HDL. And this, I don't think is new. What we observe in our study is that compare when the cells were exposed to serum before the apheretic process, this serum is able to load the cell with cholesterol. And after, when we expose the cell after the apheretic process, this serum is not able anymore to load the cell with cholesterol. This confirms the paper that I think Maria Grazia already presented and is done in my laboratory is exactly the same results. So compared to the initial content of cholesterol, when we expose to serum, we have an increase. After apheresis, we have a decrease. We confirm published results, so we know that we are using a validated method. And now we would like to investigate what's happened with LP small a. What I did, I'm sorry, we lost some access, but anyway, I would like to correlate the CLC, so the functionality of serum to load the cell with cholesterol, with the concentration of the serum concentration of different pro-atherogenic lipoprotein. As you can see here, we now found, we weren't able not to find any kind of correlation. But when I did the same correlation, so the relationship between CLC and the parameter then Federica just showed you in terms of clinical numbers, so the numbers that Federica found with the mass spectrometry, we found an inverse correlation. So the more the lipoprotein small a is small, the more are able to, the serum is able to themselves. This so is done also with the ratio that Federica just talked about, because we would like to make sure that it's not just related to some probably not very accurate measure. So I do the correlation, I did the correlation with the ratio as well, and I can see, and you can see the similar results. Then I divided control subject and patient, and the two parameters are still inversely correlated. And then I try to think about a possible average value in two populations. And as you can see here, you have in the control subject, actually you have less number of patients that are small and so are more pro-atherogenic, and then compared to patient. This measures like either Kringle number or ratio about the two peptides. So we can conclude saying that the aldehyde process reduce the lipoprotein quantity, and so the CLC as an index of pro-atherogeniity. So what I'm saying is that the quantity is still important to reduce the ability to produce foam cell, but probably it's not the only cause. So it's not the only one that causes this process. CLC is not related to the concentration of any pro-atherogenic lipoprotein, either LP small a, in patient, in this kind of patient with hyper LP small a lipoproteinemia. But CLC is inversely related to LP small a size, measured with the method use mass-based analysis that we did in pharma with Federica, either in control and in patient. So this, I think, is the first functional evidence that pro-heterogeneity heterogeneity of LP small a is inversely related to size. And this functional is a first functional validation actually of gene studies and epidemiological observation. And we can ask the study, it may be a predictor marker in patients. So to measure the size can be a predictor marker to pro-heterogeneity of this for this serum cell. I want to acknowledge, of course, all the mathematic group that participated to the study, and also Andrea Petta, who supported us. But then I think I forgot something.
Thanks very much indeed. I mean, that's a very interesting quartet of studies results. So the paper is now open for discussion, and then there will be lunch after this.
Yeah, we have the medic meeting.
Okay.
We have here the school.
Questions?
Yes, of course, we have to listen, but we have to make the story short.
Okay, quick questions from the audience for the four ladies. Okay, can I ask you each a question? Livia, for yourself, in terms of prediction, how would you judge from the literature whether the genotype or the mass is predictive? But do you think genotype predicts events more than mass? Because all the data from GWAS and Mendelian randomization has measured mass by the worst assay in the world, actually. What's your opinion?
My opinion is measure mass. It's very difficult in the big data era to analyze the results of genetics pattern, because some variants are pathogenic, but other variants are protective. So now is finished the era of the single polymorphism and the study of the role of one polymorphism is not possible now with the new genetic techniques. So I think it will be always more difficult to relate a risk with a single polymorphism or a single variant. Genome-wide studies now are the most available study in for establish a relationship between genetic variant and a risk. But in lipoprotein small a, I think it's important, more important the mass.
Okay, thanks very much. Federica, my question to you is you rather ingeniously use these two signature peptides tackling different parts of the ApoA, the variable one and the fixed one, or the invariant one. I wasn't clear from your presentation whether, because I mean you could potentially use the signature peptide in the invariant constant part to measure the entire mass of the particle, or to measure the mass of ApoA. Are you thinking of doing that at all?
No, I haven't understood very well the question.
No, you're using two signature peptides,
Yes.
one where it's variable
Yes.
in the variable part, and one
Yes.
in the invariant part,
Yes.
where it's not affected by
Yes.
crinkle size.
Yes.
So if it was not affected by copy number variation
Yes.
or genetics, because you just inherit one copy, I mean, do you think you can use the signature peptide there with the internal standard to measure the mass of the particle?
The wall.
Yeah.
Well, the problem is that peptides come from tryptic digestion of A small a. So I cannot go back. Okay, I understand. You mean to reconstruct the molecular weight.
Yeah.
But maybe there could be other types of mass spectrometry techniques to measure the wall protein. Because I've never seen many examples of the peptides are useful for quantification of concentration within a biological fluid like human plasma, but I think that it's difficult to reconstruct the whole molecular weight of LP small a. But of course, LP small a is practically impossible because, of course, there are all the components related to the glycans, the lipids, and so on. And related to just the APO small a, I should think about that, but I don't have an answer right now.
Yeah, it was just a creative question to see whether there's an opportunity, because that's the problem with the assays of LP little a is that you're doing the variability in the protein, and here you've got an opportunity to tackle an invariant part. I can share our experience with that. And for the last lady, Elda, that was a very nice presentation. You looked at LP-little-a as a determinant of cholesterol accumulation. Did you look at ApoB as a determinant of cholesterol? But this is ApoB after removing the ApoB in LP-little-a.
Yeah, no, I just used the data from the clinical part and right now from Federica analysis. So we didn't separate actually ApoB from LP-little-a, which is a good, very nice suggestion.
A good control.
And then what we want to do in the next part is to measure before and after apheresis process, which we have to do yet. Which is important because she observed actually no change in size after apheretic process, which probably doesn't affect the ability to load with cholesterol cells, but we don't know. We have to test and to discover if this is right.
Just point I think the group in INSERM in France have looked at the effects of apheresis on cholesterol efflux.
I did already actually in that paper where I show. Actually, I'm in contact with Chapman too because the efflux is various as well. after apheretic process. Actually, all the proteogenic lipoparticle goes up after maybe 15 days. So after 2 days, actually, from after apheretic process, but in my hands they still down. So the efflux is preserved like process, which is good.
Excellent. Okay, and not to leave Maria Grazia out, Zenti, I mean, just to tell us, how the study is going. Are you distributing it? Is there a potential to involve other centres in Italy, Europe, or across the world to increase the sample size? Because sample size is an issue here.
Yes, it
And
is.
who's funding this project? That's the other thing.
We are trying to enroll other patients and Claudia si farà promotrice di allargare la nostra casistica. Scusate il mio inglese, è molto limitato.
So I understand it.
Can I comment?
You're the bank. You're the bank.
If I can comment, the problem of the enlargement of the sample is the money, because genetics and pharma work is expensive.
Yeah, okay, so I have nothing to add to my co-chair comments because questions, because practically, I mean, you send the arrow exactly to the target. So thank you, the money, but in any case, I would like to express my thankfulness first to the ladies, to Professor Michel, the Vice President of our association, and to Maria Grazia Senti, who is the clinician, along with Dr. Belletti, or the Center of the Historia, who have given us the patient with more than 400 milligrams per deciliter little A, and of course to Professor Favai and Professor Vacavia for their hard work. Yes, we would like to enlarge the sample, and that I'm going to invite you to participate in this study, because this study is a full project of Mario. You are a board of the scientific committee of the organization, so the association. So please help us to increase the sample where you wish. And we will try our best to find the money and the financial support for this, because we guess this is the first time such a study is going to be developed. And so any help, any suggestion is helpful, and we are fully open to any suggestion from our scientific committee.
I mean, all I can suggest is we have to look for good friends, buon amici.
Just the last comment is, of course, we have to be grateful to Kaneka for a limited support to this study. We have to be grateful to Claudia Stefanuti Research Funds for the Department of Molecular Medicine, of course, who tried to support the study with an unlimited research grant. And we have also to be grateful to Dr. Baldini and the Brown Company, again, for his limited support, financial support to this study. So, thank you very much. Now, the streaming record will be over, and I will introduce the Myomedic Organization Assembly. We have new regulation in Italy, so we have here the fiscal and tax advisor will open the session. Then, after this gentleman will be gone, we will discuss some changes in the structure of the organization, and then there will be the lunch. So please be patient for half an hour, and then you will enjoy the lunch and the remaining sightseeing and other programs about campus. Thank you. Thank you very much. Thank you again.